My name is Mei Chin, and I'll be presenting about the analysis of titanium dioxide and zinc oxide nanoparticles in sunscreen. As the weather outside starts to get nicer, I'm sure we all want to spend some time in the outdoors. However, we should note just how the sunlight affects our well-being, and it does this through ultraviolet radiation. And ultraviolet radiation within sunlight is absorbed within our skin, and this can cause molecular damage. However, UV radiation isn't always bad. In small doses, it helps produce vitamin D within our bodies. And, the problem occurs when UV rays frequently come in contact with our skin, and its effects can be long-term and detrimental. However, these effects show up over time when our skin is not protected. So, UV rays are broken down into three different bands. There's UVA, which has a longer wavelength that can penetrate the middle layer of our skin called the dermis. There's UVB, which has a shorter wavelength that reaches the outer layer of our skin called the epidermis, and UVC, which is ultimately blocked by the Earth's ozone layer. However, UVA and UVB both reach the Earth's surface, and they're both able to penetrate our skin. So UVB rays are the burning rays, and it's the primary cause of sunburns and skin cancer. And UVA rays are able to penetrate even deeper into the dermis, or the base layer of the skin. And these rays also contribute to skin burning, skin cancer, wrinkling, premature aging, etc. So both UVA and UVB rays can also suppress the immune system, which contributes to the reduced control of skin cancer and other possible infections. So it's important to understand how we can use sunscreen to reduce the harmful effects of UV rays. So, first of all, it almost acts like a very thin bulletproof vest that stops the UV photons before they can even reach the skin and inflict damage. And they contain molecules that absorb UV and inorganic pigments that absorb, scatter, and reflect UV. And within the US markets, they require that sunscreen products contain at least significant levels of zinc oxide or titanium dioxide. So, sunscreens use a mixture of physical and chemical mechanisms to stop UV rays. And nanotechnology has developed nanoparticles that utilize physical blockers, such as titanium dioxide and zinc oxide. And specifically, titanium dioxide is actually more effective in stopping UVB rays and zinc oxide in UVA rays. And the combination of these particles assures that the sunscreen achieves this broadband UV protection. And it does this in three different mechanisms: by scattering, reflecting, and absorbing. So one of the mechanisms is called the scattering phenomenon. And this happens when the electrical dipole of the nanoparticles oscillate with the same frequency of the incoming ray. And this interaction causes a re-emission of the radiation of the particles with the same original frequency, but just in different directions. And this type of phenomenon is seen in the reactions with both titanium dioxide and zinc oxide in their reactions in reflecting UV rays. So, titanium dioxide exists in nature in various natural polymorphs, rutile being the most stable form. And the refractive index is around 4.0 for the rutile form and around 3.6 for the anatase form. So, titanium dioxide is a semiconductor with an electron structure that is characterized by its number of orbital bands that is separated by a gap energy. And within this gap, there are no molecular orbitals. So, light radiation that has the same quantum energy as that band gap is able to pass through electrons from the valence band to the conduction band. And once the electrons reach the surface of the crystals, they can take part in a redox reaction. And specifically, the rutile band has an electrical potential of 3.03 and the anatase of a 4.2. So, due to its semiconductor characteristics, titanium dioxide shows a greater absorption on the UVB range. And zinc oxide is also an excellent semiconductor oxide that possesses favorable electrical, mechanical, and optical properties. So when zinc oxide is photoinduced by solar light with photonic energy that's equal to or greater than the excitation energy, electrons from that filled valence band are jumped to an empty conduction band. And this process produces electron hole pairs that can migrate to the zinc oxide surface, and these are also involved in redox reactions. So zinc oxide also contains anti-fouling and antibacterial properties along with its good photocatalytic activity. And organic pollutants are actually diffused during its photocatalysis, and the steps are as goes. So the organic pollutants diffuse from the liquid phase to the surface of zinc oxide, and this causes the absorption of the organic pollutants on the surface. Then oxidation and reduction reactions take place in this absorbed phase, and then the deabsorption and removal of the products leave the interface region. The resulting hydroxy radicals from the photocatalysis are powerful oxidizing reagents that attack the pollutants absorbed on the surface of zinc oxide. And this reaction produces intermediate compounds. These intermediates will eventually be converted to compounds such as carbon dioxide, water, and mineral acids. And this is a mechanism of photodegradation of organic compounds in the presence of solar radiation by a redox reaction. So the main drawback for zinc oxide semiconductors as photocatalysts is their low charge separation efficiency. To combat this, doping has been used to modify the physical and chemical properties of zinc oxide by introducing impurities such as metals or nonmetals. And this is done to shift the valence band energy upward, narrowing the band gap energy to the ultraviolet visible region. And nonmetal dopants such as nitrogen, carbon, sulfur, and fluorine are used to shift this band gap. And they can also diffuse through the lattice and bind to the atoms by an oxidation process due to their extremely small sizes. Among these is carbon, which is the most prominent nonmetal dopant due to its high mechanical strength, good chemical resistance, and special electronic properties. And doping can also contribute to a greater production of hydroxyl radicals, and therefore to a high degradation efficiency of organic pollutants. So together, both zinc oxide and titanium dioxide exhibit excellent photocatalytic performances and improved activity in photodegradation. And this could be attributed to the enhanced separation efficiency of charge carriers resulting from charge transfer between zinc oxide and titanium dioxide. And together, more electrons and holes were available to decompose contaminants and enhance photocatalytic efficiency. So, to reduce your risk of skin cancer, it's important to protect your skin from the sun's UV rays using sunscreen containing titanium dioxide and zinc oxide. And as seen from the photocatalytic mechanisms of these nanoparticles, sunscreens with those ingredients are effective in deflecting harmful UV rays. However, it's seen from the graph that the absorption intensity gradually declines as time goes on. So reapplication is also important. And as of today, 1 in 5 Americans develop skin cancer in their lifetime. So next time you go out, just remember to lather up in sunscreen before going outside. And these are my list of references, and thanks so much for listening.